All right. Good morning, everyone. Welcome to NDC, and thank you for coming to video analytics for mere mortals with NVIDIA DeepStream SDK. My name is Yousry. I work for Kusu, which is a part of Manted Group. We are doing at Kusu pretty much Databricks and data engineering, but I'll be switching to something different today. So this is just a teaser about what this kind of tool can do. We'll build something similar to that today, but not really around estimating body pose or whatever. But the core idea here is about the metadata that you can get out of video streams and how you can use it in your applications to make them smart and implement advanced features. One of the cool things about this one is that, machine learning is not a silver bullet. So it depends. There is bias. There is lots of other factors. So just don't take it for granted. All right. So for the target audience of this talk, you can be a data scientist with some interest in computer vision. You can be an ML engineer who is kind of responsible for taking trained machine learning models using TensorFlow or PyTorch or whatever and deploying them to production. You can be a data engineer because lots of data will be ingested into the cloud, or pretty much anyone else. It's lots of fun, and some of the features here can be done using IoT devices, so it can be done completely using a drone or a moving car and so on. So a quick trivia time, but I'll not wait for answers because I have lots of demos. Over 50% of the cortex is used for processing visual information. So you can imagine a complexity that is dedicated to processing vision. And the resolution of the human eye, if you can treat it like a digital camera, is more than 500 megapixels, which is quite big. And our eyes can detect 10 million different colors, maybe not all people. And our iris scan is much more secure than our fingerprints due to the fact I think there are a lot more features. And we have here in Australia, Fred Hall's Foundation is responsible for eliminating avoidable blindness, which is cool. So the agenda or the scope of the talk today will be around maybe 15 minutes or so, me talking boring things, and then lots of demos showing you how to use the tool itself and how it is being much more easier than before. All right, so why computer vision? A long time ago, or maybe around 10 years ago, since explosion of deep learning, you'll find this kind of thing as TensorFlow and PyTorch and other things, and machine learning models doing image classification, object detection, object segmentation, and so on. Lots of use cases, actually. But some of the exciting ones I'd like to share here, something like this one. Before COVID was a thing, there was lots of push fires, and this can be detected easily using drones and a drone moving and capturing a live video stream and detecting if there is a fire or not. Or after every heavy rain, the asphalt will be damaged many places. Then yes, some cars or council cars can go scan the important roads or whatever and detect the problems and deploy the technicians to fix it quickly. Stuff like that. But lots of practical use cases around things like traffic management, social distancing, and whatever. So what is the major challenges with implementing some applications that is kind of treating video as input and trying to extract some insights out of the video? First thing, videos come in different formats and resolutions and compression codecs and so on. So you need something to help you not to implement the plumbing yourself. And because some of those machine learning models, like YOLO, if you heard about it, they might expect the input image to be in a certain resolution or the color channels to be in a certain order, width before height or before color or whatever. We'll need lots of pre-processing and batching lots of frames together, maybe from multiple sources, so that the inferencing can be done very quickly. Because you can imagine, a video, the minimum video now is maybe 30 frames per second. So you need to apply the inferencing at least 30 times per second quickly if you have a single source. And for sure, the inference itself, which means it is the other side really of machine learning. Machine learning, the first half is training, so you will get a good model. And after that, we'll take that model and put it in production, and then feed it with data and get the outcome. It's kind of, think about it like a mathematical function. You feed it with data, and it will return the value. So yeah, lots of models coming from different libraries with different formats and stuff like that, and you need to run the inferencing as fast as possible. So that's also a very big challenge to handle. Next one is tracking. Tracking is more about what, if you are doing a image classification or object detection using a static image, it's a single image. Yes, you will detect there is a cat here, there is a dog here. But if it is a video, if some object comes into your viewport, you need to track that this is object number 1, and they need to mark it number 1 across the whole kind of all frames until it exits the frame viewport or whatever, so that you can count people in a certain region or count cars crossing a single line or whatever. So that is called tracking, and it's really hard to achieve as well. And for sure, the last two ones is something like building some sort of smarts on top of the inference data. So the inference data could be the bounding box of an object, or this kind of, you remember the wireframes on people or whatever in the first video. So you need to implement some sort of logic based on this kind of outcome, and then maybe that will be used for notification or for taking an action within your application. And for sure, this kind of metadata, which is the output of the inferencing, you might need to feed it to something like Kafka or Azure Event Hub or whatever, Azure IoT Hub, so that it can be maybe used quickly for doing any real-time analytics, or you can keep it for historical reason and reporting. So lots of things that, yeah, if you implement this kind of application from scratch, it will be a nightmare. So we need to have something to help you with the plumbing and housekeeping, so that you can focus on your own problem only. And this is the solution here. It's an SDK from NVIDIA, and that's why you have to run it on NVIDIA hardware. So two options here mainly. Or especially for development, you have to have a laptop with RTX 2080 or 3080. Not everyone will have such thing. The other option is to use some devices called Jetson devices. I'll show you a screenshot after this one. They are not so expensive, really. You can get a good one for $1,000. And the other option is to run it in the cloud or on a server with a GPU, a suitable GPU. All right? So you need to have NVIDIA hardware, which is very optimized for this kind of use cases. But other than the hardware itself and marketing stuff, the important bits are these ones. DeepStream SDK is a pipeline of plugins built on something called GStreamer on Linux. It is a C++ library such that it will be optimized to run on a certain hardware and very efficient. So we'll have some plugins to capture and decode video from cameras from RTSP streams, and RTSP is a real-time streaming protocol, which is very common with security cameras at home and so on, or even from flat files for testing and development. And so you can capture the videos, different encodings and so on, decode it. You don't have to do that stuff yourself. Next, the pre-processing I mentioned in the challenges section. So yes, you can have multiple frames together in a single batch. You can resize all of them to a single resolution that is very suitable for your machine learning model. And then after that, you can run the machine learning inferencing. So the input is an image. The output maybe could be bounding box information. Okay. So the library or the SDK comes with a bunch of ready-made or built-in models for detecting people and cars and so on, and many other use cases we'll have a look on. But you can bring your own models as well from TensorFlow or PyTorch or whatever, or Onyx. You can convert them to some NVIDIA internal format, or you can use them with another kind of product that allows you to use the models as is. So you don't need to ask your machine learning team to do the training and then convert them to NVIDIA format. Okay? And then another plugin for doing, tracking. So till detecting this object comes here in the video stream, it will be assigned number 3, 4, whatever, and then while it is moving, it will be kind of tracked using the same ID. Then after that, the inference data can be used to build a little bit of extra logic or to be sent to the cloud or other applications to consume it. And we'll have a look on 2 examples using Azure IoT Hub and Kafka. So that's it pretty much. Do you have a question till now? Great, all good. So this is the other option for doing the development, and other than the development itself, it's more about IoT use cases. So these are similar to a Raspberry Pi board, very small, kind of, like, as you can see the dimensions here, and they're not really expensive. So the minimum one or the smallest one is around 100 USD. So shipping and a bunch of extra accessories like keyboard and stuff, it will be around 300 AUD. So yeah, pretty much doable. So you can do all that stuff that I'll be demoing today on these devices, and these devices run Ubuntu, full-fledged Ubuntu, just connect it to a monitor and off you go. And you can also hook it on a small robot car or whatever, or a drone. So lots of exciting use cases are done using these Jetson devices. So related to the development itself, unless you are extending the SDK itself, building extra plugins or whatever, there are three options. The first one, which is the easiest one, we'll go through it today in a little bit more detail. The latest version of the library or the SDK, they come up with some sort of a GUI, a drag and drop interface, so that you can drag and drop this kind of plugins and connect them in a pipeline, and you will have a running application. It was very hard before to do that, or that composer was not there in the previous versions. So you had an option for Python and C++. Python is quite good and easy, but still you would like to, you will need to write lots of code, like what to instantiate a certain plugin and connect it to the next and so on, and configure the properties. It's not really a lovely experience. This is good at least for initial proof of concept or experimentation. And then regarding to deployment, once you are done with these applications, for example, Python, you can take the Python files or compile it in a wheel or whatever. And the same applies for C++. You can take such things and put them in a Docker container and deploy to the relevant device or virtual machine. So it can be a Jetson device, or it can be a machine in your factory on, sorry, this is something that can you put in your factory or in the cloud or something like that. And for sure, this one as well, it's a bunch of YAML files that you can also put them in a container and deploy them to a certain environment. And the good thing about all of these options here, at least the Graph Composer option, this is YAML file, so it can be added to your source control, and you can track its changes and review changes and so on. It is not something like Power BI, in which you will get a binary file that cannot be inspected for code changes or whatever. All right, great. So the development workflow here is basically you will have a machine within a specific NVIDIA GPU, Ubuntu latest, or actually this is not the latest, I think, drivers, a bunch of drivers, and NVIDIA Docker to allow Docker to access the GPU, opening some firewall ports and so on. That's the case if you don't have the GPU on your laptop, like one of these kind of gaming laptops. But in our case here, the demos I'll be showing, that's a virtual machine in Azure or AWS with the relevant required GPU. And then I can connect remotely and use VS Code. So VS Code here can be used for maybe two things. One of them is that you can SSH into a certain container. There is an extension called remote containers, such that you don't have to install the SDK yourself. There is a Docker image provided by NVIDIA containing the SDK pre-installed, and then you can just create the container or launch the container and start developing there. You don't have to install everything from scratch because it takes time and a little bit ugly. Okay, so this will make development very easy. And what else? And it will allow you also to have access to that Graph Composer thing. I think that's it. So demo time. But before I start the demo, I'll show you what is our input and what we would like to do with it. So this is our input data. It can be a static file, can be a live camera or whatever. Traffic, cars, people, bikes, stuff like that. And you would like to detect moving objects, assign them a tracking ID, or count how many ones are crossing a certain line, and this kind of use cases. All right? So the output, I mean, for development, you can have the output like a live video with the bounding boxes and so on. But we'll see how to also track this kind of inference data and push it to the cloud for some extra consumption or processing. All right, so our first demo here will be just about drawing bounding boxes on top of such moving objects. All right, cool. So I'll remote inside that machine. And I logged into that machine, but maybe first I'll show you that's an AWS machine with a certain instance type containing the GPU. That's it, pretty much. And then just install the GPU driver and that kind of NVIDIA Docker thing. The specs are, the steps are on NVIDIA website, so should be straightforward. But after that, the good thing and the easy thing really is using this kind of Visual Studio Code feature called remote containers. All right, so we'll find something here showing that, okay, I'm running in a container now. And to make it running, and actually it is not only for this kind of thing, not for DeepStream or whatever. It is this kind of remote container thing is done such that you can have, okay, while you are developing for Python, for example, but this project will require Python 3.9 and this one 3.10 or whatever, so, or Node.js or Angular or whatever. So you might have to have isolated development environment fully sandboxed. So it's something that is much more powerful than our use case here, but just to mention it. So how to configure it is very easy, really. You'll have a folder called dev container, contain a JSON file, and other than the Docker RAM parameters and so on, just point it to a certain image repository, okay? So this is a DeepStream SDK 6.1 development image. It is similar to .NET. They have a runtime image in which you can just deploy and run your application, and then a development image, which is like the SDK itself, in which you can develop your applications. So we are inside that machine right now, and actually just to show you or prove you that we are running here inside that virtual machine. So to do docker ps. Okay, so there is a container running, and NVIDIA SMI. This is another command to check whether your machine has an NVIDIA GPU or not, and I think there was something Tesla T4 here. Okay, this is the GPU type. So we'll move to VS Code. Our hello world. It's around 9:20 now, and I'll see if I can do a hello world video analytics application in maybe less than 10 minutes. All right, Composer. So this is how to start the Composer. Now we are running inside that Docker container, actually. And using some black magic here and there, that kind of GUI application can be still rendered out of the container itself. Don't worry, this shouldn't break it. So the container is just a canvas, drag and drop canvas. You can just drag and drop components or plugins, connect them into the right order, and then off you go. You can have your application running. So I'll create a new graph. Call it demo 1. First thing, if you remember from that kind of challenges or plugins slide, there should be a source. In our case here, I'll pick a single source input. And then I can connect it to a certain file, but because I don't want to copy or hard code the file name now or file URL, I can just put a dummy value and I'll parameterize it later, which is a good thing such that you can just develop your applications, package them, and make them like dynamic so that they can accept a file from that location or this location and so on. So I'll put file path. That's a dummy value. Maybe you can also make it loop so that it doesn't exit the application once you are done. Oops. I mean, the mouse clicking here is not so good. But to parameterize things, you need to click on that small checkbox beside every setting you would like to parameterize it. OK. And by the way, they have their documentation is not so amazing, but when you hover over such properties, you'll get a little bit of tooltip containing some help. All right, so this is our input, a file, but it can be a live camera, or it can be some other RTSP stream. Next, we need to have something called multiplexer. So I think that's it. So as you can imagine, video output of this guy will go into the video input of the next, and so on. But in this one, I'll need to specify, I think, if I'm not wrong, this is the correct resolution of that file. Batch size here is actually an indication of the number of input files or input streams we have. And after that, we have what we have video inferencing. So I'll just search for inference. So, and it was called infer video. Infer video. Okay, move things a little bit. Oops, sorry guys. Video output, the video input here. And then, as I mentioned before, they have a group of built-in machine learning models for computer vision, for detecting objects and cars and people and so on. So you can use one of these things yourself. You'll go to model config here, right-click, and then create, and pick one of the existing models. So I'll pick a model that is detecting people and cars and bicycles, and actually detects four types of objects, not everything. And after that, we need to have something to display the bounding boxes on screen. It is not really needed for production applications that are completely running in the background and just feeding the metadata of the inferencing. But for development, there is something called on-screen display. So it will allow you to take the result of the inferencing and put it on the screen. And then we're nearly there. Just two extra plugins. So the final plugin here is the output. So you can feed the output to display in a screen directly, so it will just display in a screen. But I'm having some difficulty with that setup due to the remoting thing. The other option is to publish the output as an RTSP stream. Think about it like YouTube streaming or whatever. And it can be accessed remotely. So you can run your application on that machine and send a link to your manager or someone to have a look and review the outcome. And we'll use that one. So it's called, just go search here. Let's go back here, RTSP. There is RTSP output, and there is something called the video output, a classic video output. So connect. I hope I'm not connecting the wrong types of inputs together or whatever. And this one, you can just configure things like port number and so on. But it will be running on the current virtual machine. The final one is not really about videos. It's more about that kind of low-level library the SDK is running on top of. It's called the GStreamer scheduler. So think about it like a driver or some sort of, it's a scheduler. So scheduler. You just need to grab it and drop it anywhere. And that's it pretty much. I'll need to save my graph. I'll go to my development folder. Demo 1. It will be called demo 1. All right, all good. And then I can right-click here and export the parameters. Meaning all the attributes that we collect to be exported as parameters, there will be another YAML file containing pointers to such things so that we can tweak them. Anything like file location, a connection string of Kafka or whatever. So that's it pretty much here. I can go back to Visual Studio. If we go to demo 1 now, we'll find two new files created. One containing the graph definition. It's just a YAML file containing the names of the components and how they are connected together. It's not really magic, and you can see the dummy file path we created before. There is a parameters file here. So the parameters file, you can tweak the file loop flag so that the video will just continue forever, or the file path. So I hope I have the correct. I can grab it from somewhere else. So that's it pretty much. Go back to our machine here. Go to the parameters file. Modify the URL or URI. Okay, save that file. Create another bash terminal, and then how to run such things. So we are done with the graph composer file, or the definition of the pipeline or workflow, if you would like to call it this way. We just call some application called execute graph. It's a shell script. Give it the graph definition itself, demo1, give it the parameter file, and point it to another file that will tell if I'm running on a virtual machine or running on a Jetson device. Okay, so in our case, we don't need to edit this file. This one is provided by the library itself. All right, hit enter. Sorry, I need to go to demo1 folder. I'll do this mistake all the time. All right, you'll find some stuff happening here, and some indication that there is a port open now, this one. If I go to my VLC on my own machine, it's not really the virtual machine, it's my host machine now. And run this one, so you get this stuff in 8 minutes, all right? So moving objects, video stream, whatever the frame rate or whatever. And by the way, it's detecting 4 objects, and this is a bus, not a car, but that's another story. So yeah, persons, cars, there will be a bicycle if there's a bicycle, and there is some, it can detect road signs as well. But you can imagine, and these are ignore the video or the moving cars for now. The outcome is really the bounding boxes and the object type itself. And this is the output that you can feed to some other logic or whatever to do something about it. Okay, detect if a person is just walking in front of your gate or whatever, late night or whatever the use case really, all right? So this is the hello world that can be done in less than 10 minutes. I'll stop this one and come here and stop this one. The next one will be about applying a tracking number on top of each moving object, okay? So that you know that, okay, this is person X, this is person Y. So I will not do the graph from scratch, but I'll open it for you so that you can imagine what is the delta between the current graph and each subsequent step. So I'll come here. Maybe ask a question, please.
How did you install the graph?
It comes out of the box with that Docker image from NVIDIA. So they have Docker images containing the SDK as a runtime to run the application like this one, plus development tools like Graph Composer itself. Okay, so just to make it a little bit more obvious. But let me show you this graph first, and I'll then show you where is that container image thing. So I'll open the next graph, which is about applying tracking. So it's very similar to this one, although there's a bunch of extra things I'll talk about quickly. But the major thing here is that we have a plugin called Object Tracker. I mean, it's kind of a type NV, which is for NVIDIA DeepStream, DS it's for DeepStream Tracker. And that will do the magic for you. It will assign a unique ID to each individual object going in and out and so on. And everything else is something called cascaded inferencing. So the idea here is that once you get a bounding box around the car, maybe the next step I'd like to know the car color. The car, I don't know, the license plate. Some of the machine learning models are based on or designed such that you need to feed it kind of pre-processed data. So to detect the license plate, give me a box containing a car first, and so on. So that's kind of layered inferencing. Okay, and we'll have a look now. So that's it. The next one, it's not really a massive difference from before, just a few extra plugins. And by the way, you can implement your own logic on top of such things using Python, for example, or C++ if you want. So one of the examples on GitHub is about like this one. So it's detecting people as well, but you can apply a face, not a mask really, but what's that? Obfuscation on top of people faces and so on for privacy. So yes, you can detect the data coming from the buffer. It's called a probe. So you can connect to the data running in this pipeline, and after the inferencing is done, you can, okay, this is a face. I'll go and blur it a little bit or whatever. So let's go to that question quickly. Here in Visual Studio Remote Containers, we'll have a diff container file, and sorry, not this one. And this one, this from Microsoft, you can just Google it. It's called the Visual Studio Code Remote Containers Extension. And it is very useful for many use cases. So this image contains the runtime itself to run the graphs and this kind of applications, and to do development using Graph Composer. So yeah, that's it. What else? Now we need to run demo number 2. So the same stuff. Okay, it's running now. Need to go to this guy quickly. And you can see numbers now on top of each object. They are like what fixed while the object is moving, so they don't change. And this was a big challenge to achieve in previous versions. Plus, once the object approaches us a little bit, you will find a little bit of information about the car and make and maybe model or something like that. Okay, white, something. And you can see they have also some kind of smart thing to detect there's a license plate here. So I'll blur it. So it's kind of built in as well. So that's it related to tracking. As very important, tracking is one of the core things in the library itself, because it will allow you to count objects and do window functions and this kind of use cases. Without object tracking ID, it will be just bounding boxes of, you don't know, objects, cars, people, whatever. So tracking is really critical. So the next one is actually about taking such information and pushing it to the cloud. And I mentioned that many use cases will involve this kind of IoT devices, Jetson devices. So you can take the bounding box information and you would like to push it to Azure or Kafka or whatever. I forgot to mention, yes, they have also very good integration with Azure IoT Edge, which means that stuff can run in an Azure IoT Edge module independently and interact with all the modules on the same device. So IoT Edge can allow you to run, for example, Azure Stream Analytics on the device itself, and you don't even have to connect to the cloud. In some certain cases, you can work completely offline, especially in remote locations and so on. So next one, we'll push data to Azure. Back here. So let's open the graph, a quick one. So any question before the next demo? Makes sense? Good. So number 3. Major difference here, we have something called a message broker. So a message broker is basically around taking the output of the inferencing, the information about the bounding boxes, x1, y1, x2, y2, and object type, and whatever else, and push it to some sort of a message broker. They support Azure IoT Hub and IoT Edge by definition as well, and Kafka and any messaging broker that is AMQP compliant. So I think RabbitMQ could be an option as well. But in this case, we'll push it to Azure IoT Hub. All right. So I'll go here and just show you the, not really the connection string. So I'll go to demo 3. I hope the window is big enough to hide most of the connection string, but I'll delete my stuff later anyway. So we have the parameters here. It's not fully visible, so you need to point that kind of plugin to a certain C++ library. There is one for Azure, there is one for Kafka, and so on. And you need to provide your connection string. So there's a connection string for a device on Azure IoT Hub. And that's it pretty much. All right, let's go and grab demo 3 snippet and give it a go. All right, it's running now. I will not inspect the video because it will be identical to the one before, but I can come here. I have an Azure IoT Hub kind of extension here so that I can inspect the messages landing in a certain device. Sometimes it takes time to refresh, so you might need to jump between tabs like this one so that it will display. But as you can see here, ignore the fact that the tracking ID is fixed right now. You will get X1, X2, Y1, Y2, and the object type, okay? I have a problem with the tracking for this demo, but everything else is kind of pushed to the cloud right now. And the good thing about it, because just to mention a little bit around data engineering and so on, is that you can connect something like Databricks, a streaming application. Oops, not this one. You can connect Spark to that thing. The stream could be done right now, and display data. 1 second, let me try to run once again. It might be empty now. Or actually not really empty, but because I'm pulling here from the end of a stream, which is on Azure IoT Hub. So if the live video is done, there will be nothing to pull. So I can come here. This one is running. Okay, all good. You can go and have a look. But eventually, what you can get here is that you can feed your data. I'll cancel this one. Yes, it was displaying here. Yes, you can feed it to the cloud for some application like Spark or whatever to be running 24/7, collecting this kind of streaming data and doing some analytics in real time. They call it sometimes a hot path. And then the data can be, let me run this one for now. I just want to show you how the data is being kind of ingested on the fly. This one's still running. So yeah, stream is initializing. And then data can be fed to something like a Delta Lake table, and it will be appending forever. You can implement something for historical analysis or something real-time analysis. So it's feeding data right now. If we run this kind of query to count how many objects are there, how many people, how many vehicles, you'll find 25K or 28K. If we run this one once again, we'll find this one, still 28, maybe the frame, not really. Maybe still like what bootstrapping or whatever, but yeah, okay. Let me run it once again. Yep, I think it has increased now, and if we run again. So what we're doing here actually is parsing this kind of, yes, it's increasing now, as you can imagine, 38. It's taking that kind of JSON information. You have seen it a few minutes ago, which is this one. Let me disconnect this guy. Do I have an option? Oops. To disconnect. Yes, it can take that JSON, parse it, and then store it into a database table or a lake table. All right, and then you can use it for real-time analysis or historical analysis. All right, cool. That was with integration with cloud and things like Azure IoT Hub. The next one is a little bit more advanced. It's about implementing some features like switching your machine learning model on the fly or enabling recording. So for example, I think most of our security cameras or whatever at home, when someone passes or some object is moving in front of the camera, it will auto record by default, okay, for 10, 20 seconds or stuff like that. The important thing about the library here is that you are feeding the video to the library itself, whether it is running on a certain device or virtual machine or in your factory or company or whatever. You are not feeding the whole feed to the cloud. There will be latencies, there will be cost for network transfer and so on. So the library is doing everything kind of internally. So if you'd like to run it completely outside of cloud integration, you can. And that's the point really about you can connect to this library, send and run the library, get your inference results. You can send them to the cloud, but you can also send messages from the cloud to your device to do something. Like as I mentioned, recording based on certain events or whatever, or sometimes you'd like to maybe switch the machine learning model on the fly. So you have a machine learning model working in daylight conditions, but after sunset, you would like to switch it to another model that is suitable for nighttime conditions. So this kind of things can be also done. So we'll do some sort of on-demand recording. I'll go to my environment here. Maybe, yeah, I enable this one to run forever. Yes, and that's why it is running here. Okay, another session here. So this time, it's something called smart recording. Data will be fed to Kafka in this case. And I can go to Kafka, create another topic, and in that topic, I can drop certain commands to start recording or stop recording. So you can see here, there is a folder called recording. It's empty, nothing there. I'll go do some preparation now. So because this demo was designed to work on an RTSP input. All right, oops, this is not working. Give me a second. Might be some port is being, maybe some port is consumed or whatever. And what is the error here? Connection refused. So maybe I cannot do this one. Seems that there's some port stuck here or there, but the demo here will be very similar to before. The data will be pushed to Kafka, similar to Azure IoT Hub. And then what I'll be doing here is go to Kafka. I have a Confluent kind of Kafka as a service instance in Azure as well. And go there. There will be two topics. One to receive the messages you have seen before, like Visual Studio Code, and one to send commands. So you can send commands from the cloud or from your own application using whatever library you would like to use to the device itself. So the device can take the message and act accordingly. So you can have stuff here like two topics, one topic for, what is that? Is it my internet or what? No. All right, one topic for receiving messages and another topic for commands. And here you can just come here, produce a message, send a message in a certain format, and the message will be sent to the device. And then you can, there are some built-in out-of-the-box features to do smart recording or switching models on the fly, but you can write your own code as well to receive a certain message based on whatever command names or stuff like that, and then do your actions. I mean, the plugins here are configurable so that you can change the properties of a certain plugin or whatever. So yeah, it will allow you also to interact and control the behavior of the library in the runtime if you'd like to do that. So we'll go to the next one, which is, I think, a cool one. Go back here. I'll open the container, sorry, the composer once again. The next one is about applying a little bit of extra analytics on top of this kind of bounding boxes and tracking IDs and so on. So that's it pretty much. It's called NVIDIA DeepStream Analytics. It comes with a bunch of features for detecting if, how many objects are crossing a certain line. You can define the line by specifying, providing a config file containing the X and Y coordinates of the line in your video screen. It can count objects and stuff like that. I think there is a bunch of other features, but these are the ones I have here in the demo. So let's give it a go. I'll show you the config first so that you can imagine what I'm talking about. So you'll drag that kind of component here and create a config file containing, where is demo 5 here? Containing coordinates, for example. So this is something called region of interest. You need to provide the coordinates, kind of a rectangle or something like that, or provide the coordinates of a certain line and another line as a direction of movement. And then it can count how many objects crossing that line or how many people are in this kind of region now. So yeah, social distancing or traffic management or whatever. Let's give it a go. So that was a smart recording. As you can see here, this is the command and the small JSON messages that you can send to the device. But unfortunately, I'm not lucky with this one now. All right, cool. Come here. All right. You can see here there is a count here about how many objects are kind of exiting in this direction. All right. It's not very accurate. The other bounding boxes can cross it or something like that. But anyway, there is something here about how many people are in this region of interest. There is one right now. This is not really a person right now. But just wait a few seconds and you will see that when a bunch of extra people come here, that count here will be 3, 2, 3, 4, whatever, okay? So yes, you can do this kind of thing, put a bounding box here and count how many objects are inside that counting box and do whatever logic you would like to do on top of that. And this logic is about moving objects in a certain direction and crossing a line. This feature is kind of one of the features available in Azure Video Analytics service itself. It's kind of, one of the cool things over there as well. So these are some of the extra features that you can get out of the box of the library, and you can build your own if you want, based on the inference data. It will be a little bit more advanced, but still doable. And as you can imagine here, lots of the plumbing is done for you. So you just need to focus on your own problem, bring the proper machine learning model, and just use it and build on top of that. So quickly, end of demos, 4 out of 5. That's not too bad. Let's talk a little bit more, not too much really. Challenges about using such SDK. First, the documentation is very dry. They improve it over time, but sometimes you need to jump here and there such that you can connect the dots. And NVIDIA is not doing things in open source like Microsoft, so it's a little bit hard to investigate the source code itself or understand what's happening behind the scenes. And their support is suboptimal. It's not like you will ask a question in Google and you will get a quick answer on Stack Overflow. You need to go to their NVIDIA developer forums and so on. And sometimes they take time to respond. Sometimes there will be no answers. They will just point you to documentation pages and off you go. So you can live with that, but it's not so good. And the learning curve is a little bit steep, especially from previous versions because there was no graph composers. Or at least if you'd like to implement sophisticated use cases, you will need to have people very good with Python or maybe C++ in the worst case. But maybe most of the common use cases or the easy ones are pretty much easy to be done. So most of the source code and this kind of thing like pointer to the Docker image for development and so on, and source code files. It's not really source code, but just Graph Composer files you can use as is, and they are actually provided part of the documentation itself. You can find it here. Okay, this is pointing to a GitHub repo, all right? And I think that's it. I'll be happy to answer some questions. I think we have around 9 minutes or so. Yep.
If you need a custom model,
Yeah.
how can you use the composer to do that? Is there
the composer is not, thank you. The composer is not the tool to control or tweak how to use a custom model or not. There are two options. The composer is just about to bring the plugin that will do the inferencing, and then that plugin, you will point it to the model. So two options there. You can bring your own, maybe, for example, TensorFlow model, and they have the tools to convert it to something called TensorRT. Think about TensorRT like an optimized version of your own model by pruning lots of things in the network or whatever to make it run very quickly. Okay? So this is one option. Takes your model, convert it to their own format. The other option is something called Triton Inferencing Server, and it is actually the back end of Azure Machine Learning Services. Triton Inference Server. And it's a good thing it's open source. So this one can work also with the SDK, and it can run directly on models from TensorFlow and PyTorch and Onyx and all these things. So yeah, you have two options, but this will be a little bit slower than the first option, because the first option is very optimized. The network will be converted in a format that will run efficiently on the hardware. So for example, if you'd like to run on a virtual machine, they will give you a version for the virtual machine. If you'd like to run on a Jetson device, they will kind of optimize it or compile it for that device specifically, for the hardware itself, like hardware-specific versions. But this one is hardware agnostic, so it will be a little bit slower, in case you are asking your performance is a major factor to you. Cool. So happy that you have, maybe hopefully you have learned something new, and you can do it yourself. If you have Azure or AWS access or whatever, you can go create a virtual machine and maybe give it a go if you want in your free time. It's lots of fun. My kids at home are quite excited whenever they see these kind of cars and people moving and bounding boxes, and yeah, it will be lots of fun. And thank you so much for coming.